Okay, welcome everybody to my talk for Open Source 101. My name is Clint. I work for a company called NetFoundry. We are sponsors of this project that is free and open source called the OpenZiti project. You can find it on GitHub. And this little guy right here, he is Ziggy. He's our mascot because every open source project must have a mascot. And today I'm going to be talking about application embedded zero trust. And what does that actually mean? So we will go through the state of the art of what current networking security setup looks like. We'll take a look at some zero trust principles. Then we'll look at what it means to add a zero trust SDK into your application and what kind of superpowers it can give it. And then we'll talk a little bit about some of the existing applications that we've already added a zero trust SDK into. And you'll see those in a bit. So let's talk about the current security setup that is considered good enough for today's world. So here you can see we have an example of a basic network. There's a primary office building with employees and devices in the lower left of the screen. We're going to keep this network small. So there's a single main location. You can see maybe there are some IoT devices in cars. Maybe there are some users on cell phones. Maybe there are some users at home with their own home network. We're going to focus on the lower left though. All right, so I've taken and I've replaced all of those buildings with this wall and moat, because this is what you think of, generally speaking, when you think of what current, maybe not best of breed, but what most people think of as good enough networking security. So you think of a castle, you think of a moat, you think of these general defenses. So oftentimes that moat can be breached, that wall can be breached through a drawbridge, what we might call a firewall. The key part of this diagram is that if you have gotten behind the walls, if you've gotten over the moat, then you are considered trusted and all of your data can be sent to any other machine on that network. I think we all realize that this is not exactly the best situation in today's world. And so let's see what we can do about it. Well, what we decided was, hey, let's take all those protocols and let's make them secure. So now you can see, if we take a look, all of our little connections, they have a little secure icon on them. They're all locked. So if we're using SSL, if we're using HTTP, that means use HTTPS. If we're using FTP, it means use STP, SFTP or SCP, something that is actually secure. Take those insecure protocols, make them secure by adding some encryption around them. This was a good idea. And 5 or 10 years ago, there was this project by the Electronic Frontier Foundation called HTTPS Everywhere. It said, hey, I've realized that you're trying to go to a browser destination, but that destination that you typed in was HTTP : So we're just going to automatically upgrade you to HTTPS because we see that the endpoint on the other side supports it. That way, we're doing the hard work on your behalf of figuring out that there's a secure way to send this traffic, and we'll just automatically upgrade you. On the other side of that is a project called Let's Encrypt. Let's Encrypt is a nonprofit certificate authority. Its whole purpose in life is to make it affordable and free for people to obtain a legitimate certificate, one that is actually trusted by your operating system. And as of a couple of years ago, I believe Let's Encrypt Root CA now ships with all major operating systems. So if you get a certificate from Let's Encrypt, you can trust it. So once we have these secure protocols in place, that means now that when a attacker tries to attack, they're going to get onto our network. Like we can see here down in the lower left, we can see an attacker has breached our walls. They've crossed the moat, and now they are free to roam about our network. But we're using secure protocols, right? So everything's fine. So when this guy sends his malicious payloads to his target machine, well, maybe that's not so fine. So how did this happen? Well, it could be that that target machine was using a really old and insecure version of encryption. Maybe it's been broken. Maybe it's used terrible passwords. And even though it's a secure protocol, you can't snoop the traffic on the wire, you can still compromise that target machine. Well, that's a real bummer. So how are we going to fix that? Well, in case you didn't realize it, this is the exact way that VPNs work. So if you get onto your network you are basically given access, free access amongst the VPN to wherever you can access. So there's no idea of securing that horizontal movement. And so you really want to try to avoid and limit how much horizontal movement there is. Um, so the next thing, what would happen? People would decide, hey, let's try to limit that horizontal movement. So what we're going to do is we're going to take our little mascot, Ziggy. We're going to put him in a policeman's outfit. And we're going to say, okay, Ziggy, your job now is to make sure that none of this traffic can get from the attacker to that target computer. This is called microsegmentation, and that works really well. So we can declare victory, and we've solved our networking problems. No worries, right? Of course, we know that's not the case. So what's going to happen? This attacker is going to go out and find that there actually is another laptop, which needs not only access to this light blue network, but also the dark blue network. And what are they going to do? Well, they'll try their best until they compromise that machine, and then they'll just use it to continue their expedition, finding that target machine that they were after all along. And that's basically exactly what attackers will end up doing. In fact, this happened very recently, and it's been in the news. Maybe you've even read about it. So let's look at how Zero Trust might be able to help with this situation. Now I'm back to that regular overview again. You saw that we had that castle and wall mentality and how it's just not good enough. So how are we going to defeat this horizontal movement? What are we going to do? What security layers can we add in to help us become more secure? Well, what if every single one of these devices had a firewall on it? And almost undoubtedly, every device that you have right now has this firewall. But oftentimes, there are ports that need to be opened up. There are holes in that firewall that need to be out there. What happens if the network actually understands you can't even get onto the network unless you have a strong identity? So now, if I don't have this strong identity, I can't even get onto the network. I can't even access those firewalls. I can't get to those open ports. So in order to do that, we need to bootstrap trust. Bootstrapping trust is very difficult. This is actually the flow which the OpenZiti project follows. And you can read all about that on this blog post down here. There's actually 5 parts of bootstrapping trust. Very thorough, definitely worth the read. So let's say we have given all of our identities, all of our devices on the network, and a strong identity. And now this attacker decides that they're going to go and they're going to plug their computer into the network and get an IP address. Well, if I have this idea of strong identity, the network is smart. It knows that that attacker can't even send this data across the network. It can't even access something else because I'm authorizing that endpoint before I allow connecting to that network. And that's called device identity. Well, great. That's a fantastic zero trust principle that a modern network should have. So what's going to happen? We could declare victory and we just go home again. Of course not. We can't declare victory because these attackers, they're always searching. And so what are they going to do? They're going to find a device that has the correct strong identity. So now we have our attacker. They have found that device, and now they're going to actually compromise the machine so that now they can do their nefarious deeds. So here we are. We're going to send that traffic, and now this attacker is able to send the traffic because they're on a machine which has that strong identity. Well, what a bummer. What are we going to do to prevent this? Well, now let's introduce the next zero trust pillar, least privilege. This said, what if that network that understands these strong identities, what if it actually understood what machine that you're targeting? So if you try to send data to a machine that you're not able to send data to, well, the network will prevent you. That'd be pretty neat. And that's what we have here with least privilege. Here, the network knows that the machine, which is sending the traffic, the compromised one in the lower left, does not have the ability to access the machine in the lower right of the enterprise network there. Well, great. We can declare victory and move on, right? But no, of course not. Now what's going to happen is this attacker is going to find a machine which does have the ability to communicate to that machine on the far side. And if that's the situation, well, then we're in trouble again because that machine's going to get compromised and the attacker will just continue attacking. Okay, so application embedded zero trust. What does that mean? Well, before we can talk about application embedded zero trust, you'll hear me use a word called the overlay. As we just learned, every network is basically susceptible, and that's a core principle of zero trust. It's probably the fundamental principle, which is trust no networks. Always authorize before you connect. Always verify that strong identity. So we can basically treat the entire internet as though it was our underlay network, the actual piece of machinery, the Ethernet cable, the Wi-Fi signals. We'll just treat the whole entire internet like our underlay network, and we'll build our overlay network on top of just the internet. And so we'll call that the ZD overlay network. And what we'll need for a ZD overlay network is a few pieces. First piece we need is a controller. The controller's job is to basically be the configuration plane. It's responsible for making sure you have services, and we'll learn what services are in a bit. And it's also a central place for establishing identities, users, the nodes of the network, etc. Part of those nodes are routers. So we need things that we call edge routers. We need things that we call transit or fabric routers, or just other edge routers. They don't have to be they can all just be edge routers. An edge router is a little bit special in the overlay parlance from a zero trust OpenZiti project, because it is basically the point of contact into this fabric. And this fabric will then go through and mesh itself. So what that means is every router will try to connect to every other router, which are advertising, to form a mesh network. And those mesh networks are all going to be formed over mutual TLS links, which means when the edge router tries to connect to another edge router, say this bottom connection down here, it will present a certificate. The router will verify that the certificate presented is the correct kind, and only then will a TLS connection be established. So the connecting side also needs to provide a certificate to the connection side. And ZD overlay network will actually create a fully formed mesh based on how you configure it. If you wanted every single router to listen, as I have shown here, you can have every router connected to every other router and make a really interesting topology for your network. And that's basically what an overlay network is. But that's useless without actual endpoints. So now we have these things we call endpoints. And I've cleaned up the diagram a little bit as well. It's a little bit busy with all those connections and all those little lock signs. So here you can see what we're doing. What we really want to do is we want to bake a OpenZiti SDK into an application on somebody's computer or on their phone, send it across the network, and get all that data into the API that we want to target all along. And so that's a little basics about what an overlay network is. So sometimes when you start talking about zero trust, you'll start to wonder exactly what does zero trust mean when it comes to the network. And here's a good little overview of the slides I'm going to show you in a second. So zero trust network access. This is something we call when you have a ZD router on one side of your network and a ZD router on the other side of your network. Here you're trusting, your trust zone is everything outside of the zero trust gray bucket. So everything outside of the zero trust zone, you are effectively trusting. You're trusting the device, you're trusting the applications on that device, you're trusting that device host network, and you're traversing your local network. Now, if you're at home, like I am, maybe your local network isn't so big. But if you're at an office where there's lots of horizontal capability, you might be putting a lot of trust in your network. Same is true for the offload site. You offload onto that local network. You can consider this to be like private networking in the cloud as well. This literally does not matter to a OpenZiti overlay network. Wherever you deploy your device does not matter. All you need is outbound internet, and you can make a zero trust connection. So this is the first layer that I would say OpenZiti would consider to be some zero trust. So let's make this a little bit less trusting, a little bit more zero trust. You can actually take and run an agent on your local device, as I'm showing here, or on the server's device. We call these things tunneling applications. And you can have your trust zone be reduced dramatically. Now you're only trusting your local machine. You're only trusting the device that you're trying to send data from and the device you're trying to offload onto. You can configure a zero trust overlay network to offload to local host, meaning you can intercept local host and offload to local host. You're only trusting that host network. And of course, there's one step further. you can actually take that Zetified SDK and drop it directly into your client app on the left or into your server app on the right and dramatically reduce how much trust. You still have a little bit of trust shown because you still have to trust the operating system, right? You can't, you'll never get away from trusting the operating system. You'll have to trust just this one application, but all the other applications on that computer are totally irrelevant to your zero trust. And we'll see more about that in a second. So what does it mean to be application embedded? Well, I just kind of touched on that fact a moment ago on that previous slide. We have our attacker, we have our target machine. We're going to just focus on those two things because what we want to do is we want to take an application represented by this package, take one of those SDKs and smush it inside of that application and now make it's got a lock icon. So it's now safe and secure. It's a zero trust application, has zero trust baked into it. All those principles, device identity, authorized before connect, least privilege. Now we're taking that and extending it all the way into your application, all the way into your operating system, not just stopping at the network. So we're bringing all that zero trust goodness directly into the applications in your computer, which really is the next phase of zero trust. So what happens if we have 3 secure apps on a compromised machine? We have an SCP app, a SQL app, and an FTP app. Well, if SCP sends data to SCP, that's perfectly fine. If SQL sends data to SQL, perfectly fine. If FTP sends data to FTP, perfectly fine. But what's going to happen when this hacker tries to use the SCP application to send traffic, say, to FTP? Well, SCP can't address FTP. So that little built-in firewall, that zero trust, that least privilege is baked into the application itself. The SCP application doesn't even know how to address the FTP server. Of course, the same is true if the SQL Server app tried to access FTP or if the SQL Server app tried to send traffic to SCP. It's all safe and secure, locked behind those zero trust principles baked into that application. All right, so this is where the OpenZiti project comes in. And this is where we start to learn about those superpowers of an application embedded network that I was talking about earlier. All right, what we have here, we have 2 cars. On the top, you see the Beast, and on the bottom, you see what I've referred to as the Mad Max version of a car. On the top, we have security baked into the car itself. Those doors are bulletproof, the windows bulletproof, the tires can't be shredded, right? Lots and lots of excellent security, all baked into one sleek package. Why is that cool? Well, imagine you were the user. Imagine you were the United States president, the guy who rides in this car, in that thing called the Beast. Well, if you're just riding in it, you just know that it's a nice car and it rides nicely, right? You're just a user. You don't have a clue that all this fantastic, super secure stuff is going on inside of that car. Now, contrast that to the Mad Max style. We call this at NetFoundry build it in versus bolt it on. I think it's obvious which one is built in and which one's bolted on. But in case it's not obvious, on the bottom, all we have is armor. It's everywhere. It's kind of been slapped on. And this is what happens to networks. This is what you have to do. This is what we've had to do. Every new breach comes with a new problem. So we come up with interesting ways to bolt security around our network itself. We come up with firewalls. We came up with web application firewalls. We came up with intrusion detection, right? Lots of things are built onto our network as opposed to built into our network, bolted on versus built in. So that's the first thing that you get with OpenZiti. That's a pretty cool superpower. You don't even know it's there. Your users don't even know it's there. The next thing as a developer is addressability. So here you can see before OpenZiti on the top and after OpenZiti on the bottom. On the top, if you're really, really lucky, when you send an envelope, you send it to a DNS server, and that DNS server resolves to some IP address. And if you're lucky, it all works, right? Because sometimes DNS might not be the same from your local machine to your other device in your other network somewhere else. And then if you're trying to decide who this package is coming from, usually you have one option and you have an IP address. So the network has just the IP address to base itself from. With a ZT network, you can actually take that many steps further. Now you can just say, I want to send this payload to Jenkins. And you can say this payload is coming from Clint. Because of that strong identity, because it's baked into the network, you full well know that this is going to Jenkins from Clint, which is a really cool feature. You don't have to worry about IP address. You don't have to worry about DNS names. You can just call it whatever you want to call it. And because you can call it whatever you want to call it, you can make up any name. It doesn't have to be a DNS name, my application server. It can just be Jenkins. It could just be Clint's Jenkins, right? It's just a name. You can make it up. So it's also not just for clients. A lot of times we think of these zero trust principles. We think about them at that dirty site like the Starbucks, where my users are going to go and get on the Wi-Fi. But it's not just for the user going to Starbucks. It's also for your data center. So with a OpenZiti SDK baked into your application itself, you don't have listening ports. And that's incredibly powerful because now you don't have complex firewalls that to keep up to date. You don't have to wait as a developer while the network guy goes and provisions some kind of MPLS link or fast connect or VPN. Ooh, that word. So yeah, we have no listening ports. That's pretty amazing. On top of that, because there's no listening ports, your typical kinds of attacks are just, not as easy to accomplish. Some of us may remember a particular vulnerability that came out around Log4j and Java recently. So when I have an opening firewall hole, even if it's a nondescript application in my server side, that attacker is absolutely able to attack that app that is compromised and become horizontally mobile and go and attack something else. Now, contrast that with OpenZiti. With OpenZiti, you have to have a strong identity in order to get onto that network. There are no listening firewall, no holes in the firewall for the attacker to go through, no listening ports. The attacker would have to compromise one of those devices over here in order to become nefarious. OpenZiti doesn't protect against a nefarious bad actor, but it makes it so much more harder. It's security, as we know, it's all about defense in depth. It's about making it that much more difficult for a user or for a attacker to compromise a device. OpenZiti makes it so much harder. Another superpower, since this is an addressable network, now your server can actually address the client. If you wanted the server to reach out and contact a client, it can. You don't need HTTP long polling for those of us who come from an IoT background. You don't need WebSockets. You don't need server-side includes, not includes. There's another one, server-side events. You don't need that sort of stuff. You can just have the server directly reach out. It can be any kind of connection that you want. It doesn't have to be HTTP. If you want to make it SCP, by all means, it's your connection, it's your data. You do whatever you want, use whatever protocol you want. You also get end-to-end encryption for free. An OpenZiti SDK comes with end-to-end encryption by default. You have to go out of your way to turn it off. It uses libsodium, which is a nice library because it's built for smaller devices. And it's built around Cha-Cha-20 Poly 1305. So if you want to look that up, it's kind of interesting, fun stuff to read about. How does that algorithm work? But you get that for free in an OpenZiti solution. Port inference. If you simply take a port sniffer and bring it to any network, you're going to find lots of information about that network. You're going to find what's attackable. You're going to find targets of opportunity, where people are sending their data to. Well, with an OpenZiti network, HTTPS is clearly an important port, right? And with an OpenZiti network, we actually synthesize all of those ports, all of those protocols into the same port. In this case, we're using port 443 because that would be a really good port to use. It's ubiquitous. It's everywhere. You're not even surprised when you find port 443. We talked about the HTTPS anywhere, automatic upgrades. This is so ubiquitous, everybody expects to find port 443. So by synthesizing all of those ports across one connection over port 443, we make this port inference impossible. You cannot know where your users are sending their traffic to by simply looking at the network. And it's really easy too, right? So here I'm showing the OpenZiti JVM SDK. You can see the before code looks basically the same as the after code, but let me just make it really easy for you, because realistically, before, you need to know the IP address that you're going to bind your server on, and you're going to need to know the port that you're going to bind on. And that's fantastic if you happen to know what actual IP address you're going to bind on, as well as what the port number is. But I've been in situations where my network administrator decided it was a good idea to say translate port external port 8443 to internal port 443. And so I was happy listening on port 443 and never knew, or 8443, and never knew that people were trying to send traffic to 443, and none of my traffic landed at my server. You don't have to deal with any of that in an OpenZiti network. You simply have to say, let me listen on a service, and this is the service name. And it's really that simple. You now have a server ready to accept requests. So let's talk about a few existing Zitifications that we have out there. You'll find these out in this place that we call the OpenZiti Test Kitchen. And the OpenZiti Test Kitchen is where we have all of our repositories on GitHub that you can go and see these Zitifications. Let's talk about a few of them. One of which is ZSSH. And you might be asking yourself, why even bother Zitifying SSH? Well, it's for one simple reason, right? With ZSSH and with SSH, you are going to have a hole in a firewall somewhere. It will be something that you will have to maintain. There's just no way around it. Even if it's a bastion, something will be out there listening on the open internet, being attackable on port 22. With an OpenZiti network, of course, you don't have to bother with that. Because there's no hole in the firewall, you cannot attack that SSHD server. You can't take it offline with a simple DOS attack. SCP is the same sort of thing. So SCP will just go over the same port 22. And here's a good example of using ZSSH and ZSCP. The key things here, another superpower of that addressability that doesn't really register unless I point it out, which is up here, you can see I am ZSSHing, providing that strong identity file using the service that I want to use. And then I'm providing the username of the remote machine and the remote machine I want to SSH to. Looks just like regular SSH minus some of the stuff over here, right? What the user is, where I want to SSH to. Only take note of that ZSSH server. It's different. That is actually the identity known on the ZD network, on the OpenZiti network, that you want to SSH to. This is something we call an addressable terminator. So this is how you will get your traffic to an identity on your network. You don't have to make 1,000 services if you have 1,000 users. You can make a special kind of service, which allows you to dial an identity's name directly. And you can obviously see, I've called this ZSSH server. You can name it whatever you want to name it. The same is true for ZSCP. Here I'm SCPing Ubuntu again, ZSCP server. That's the name of the identity I am SSHing into, and SCPing, and it looks identical, works identical. Mattermost. So here at NetFoundry, we chat, and when we chat, we don't use Slack. We actually use Mattermost, which is a cool chat app that is exactly the same as Slack, but totally protected on a ZD network. Part of being a developer is getting notifications when people push or make commits or whatever. So in order to get our traffic from GitHub or GitLab, we had to make some webhooks. So out here, you will find the GitHub and GitLab webhooks, and this is what will happen. It'll send me a message in my chat app, and that allows the servers out in the cloud, the GitHub and GitLab, to actually send directly messages into my Mattermost. Generified JDBC. This one's really neat. This is a different kind of Zitification. This is a Zitification that allows us to provide basically a plugin. And why it's really neat is because I can take a Zitified JDBC application and drop it into my IDE, in this, SQL IDE. In this case, I'm using DataGrip, which is from JetBrains. And you can see up in the upper left-hand corner, it says ZD Oracle. So I have, it's not an Oracle driver that's been Zitified. It's the it's a driver that actually knows how to poke and prod the actual driver in the right ways. You can see the driver is called OpenZiti, and I just have to give it a special JNDI JDBC URL. I just have to give it a special JDBC URL so that it activates the driver. And then we will go out, turn this into a true zero trust connection and send that data. Why is this neat? This is so neat because when I was providing production support to my databases, I always have to get on the VPN before I can look at the production database. With a Zetified JDBC driver, I do not have to do that. I simply open DataGrip and connect. Because I'm using the Zero Trust Overlay Network, it is already on the VPN. In this case, it's the Zero Trust Network. So it's baked all the way into my IDE. There is no client necessary with a Zetification, with a JDBC, ZDBC Zetification. Really cool. It's not just for Oracle. That's just one. You can see this is Todd's Postgres. This was running in his Docker container on his computer. Same sort of setup. I can select from the table and it all is the same, just different. So we're not Zetifying the driver. We don't maintain the driver. We Zetify something that knows how to poke the driver, which is also cool because it means very low maintenance from our perspective. kubectl, if you aren't familiar with Kubernetes, you probably should get familiar because it's pretty hot. And kubectl is what you use in order to connect to the Kubernetes API. So generally speaking, you would use a kubectl to contact the Kubernetes control plane. People usually have to put the Kubernetes control plane on the open internet somewhere and then rely on TLS connections to keep it safe and secure. With OpenZiti, you can actually take and install into your Kubernetes cluster a node that effectively acts as an ingress controller, but it's a zero trust ingress controller, one that only is accessible from the overlay network. So you can see here, I have that fabric we talked about. And on my computer, which is Windows 10, I have two choices. I can use the unmodified kubectl, which will go through one of those tunneling apps and then across the overlay network. Or I can use a Zetified kubectl and just directly talk right to the overlay network and control my Kubernetes cluster. Really neat stuff. Of course, Helm is also pretty popular in the Kubernetes world. So if you were looking to deploy a target using Helm, you could use a Zetified. Oh, I should mention, this is cool because you don't have to expose your control plane anymore. And there goes my kitty cat. You don't have to expose your control plane. You can do it only entirely over an OpenZiti connection. Same is true for Helm, which is pretty neat. And then also Prometheus. So we're working on right now coming out with a blog post for this, which will show you how you can monitor anything, anywhere, wherever you've deployed your Prometheus, you can access it. So if you had two different data centers and you're trying to federate into Prometheus, you can absolutely do that. Now, application embedded zero trust is a journey. This slide represents the path, the longest path on the globe, which you can walk. And so that's kind of like the journey for zero trust. You're not going to get to zero trust nirvana by adding a zero trust SDK immediately, or unless you have total access and it's total greenfield, in which case, awesome, take that SDK and jam it in. But most likely, you're going to have apps that you're going to want to apply all these great zero trust principles to, but you can't actually change the source code, or it's just too much effort for you to change the source code right now. That's where tunneling applications come in. If you remember way back in the beginning, I talked about those three slides, the zero trust axis, the bigger zero trust axis, and the biggest zero trust axis. Well, this is where we get that second tier. These are the applications which run on our local machines and provide us that zero trust access. These things are really nice. They have one that's just killer feature that everybody probably wants: private DNS. What do I mean by private DNS? Well, lots of people talk about how DNS is a particular problem for them because they don't want their ISPs knowing about, what websites they might be going to. Well, with an OpenZiti network, with a tunneler, and we have tunnelers for all the major operating systems, including mobile, as I showed you before. But with a tunneler, what's really cool is you can just make up a name. So if you want to use, Bodie McBoatface as a DNS name, you can do that. If you want to use Fluffernutter or Google.com, you can do lots of interesting things with a private DNS server. These are also, they don't need to be a top level domain, which means if you try to get a real DNS name, you're going to need one of the TLDs that exists, a .com, a .org. There's a whole bunch of them now. There's a few extras, but with a Ziti tunneler running, you can call it whatever you want. It's also entirely local. It never leaves that DNS request. I mean, it might leave your computer if it's not one that you're getting intercepted for, but if it does get intercepted, which of course these other ones are all just totally made up, they're fictitious. Well, mine is google.com. I guess that's real. But if you are intercepting these locally, they stay local and are totally private. And since they're part of the Zero Trust overlay network, that means we can remove them at any time. If this identity no longer should have access to those particular DNS entries, then you can just remove that identity from the Zero Trust network. And now they no longer are accessible. They're no longer addressable. They're no longer resolvable. And then, you can keep thinking about interesting, fun ways that you can mix and match. You can have your overlay network. You can have Windows running on one machine. You can have Mac running over in the West Coast somewhere. You can use your Zetified key control. You can run this stuff out in the cloud, wherever you want to run it. So this is not a passing fad. If you go out and look at the whitehouse.gov briefing, you can see they actually mention Zero Trust. And I'm going to make it easy for you. They mentioned Zero Trust 11 times. And when I made this slide was a while back, and they've actually continued to double down on this whole Zero Trust idea. They also have a really nice publication about the maturity model. You can go out and read that CISA.gov down here. And you can see we covered a couple of these pillars: identity, device. Definitely thick reading, but maybe skimmable. So at this point, I know you're thinking to yourself, geez, that sounds great. How do I get this? Can you put it in my shopping cart? Can I take it home with me? How do I bring this home? How do I use it? Well, you can go out to our landing page, which is impossible to read maybe, but it's openziti.github.io. Should be very easy to remember. We have all of our documentation. We have just quick links up here. You can click on the docs and read about Ziti. You can start building your own network right now. So if you want to run everything without running Docker, you can run everything without Docker. If you love Docker, you can use Docker. If you want to use Docker Compose, I have a real nice Docker Compose file that you can pull down and start right now. Or if you want to just host it yourself somewhere and you want to, maybe start deploying this thing and put it in production immediately, great, go ahead and host it yourself. And then there's a bunch of SDKs that you can click on. All these are links that you can click on to bring you to the CSDK, the Go SDK, Swift, Android, Java, Node, C#. Got lots of languages, not all of them, but quite a few. And if you can always go back to a foreign function interface if you don't see your favorite language. And of course, help us out. If there's a problem with the doc, you want to improve the doc, go ahead and put a pull request up. It's all open source. Here's our socials. You can see NetFoundry is the company that sponsors this. I'm Clint. You can contact me at clint@openziti.org. We have a bunch of socials. We have a great YouTube channel that has a fair amount of content getting produced. We have a couple Twitter handles. We got a discourse group. If you have any questions, ask in the discourse group. It's better than Slack, better than Mattermost because it's searchable. So this is another one of those things that actually goes right into my Mattermost. I will get notified immediately if you post out there, post a question. You want to check out that OpenZiti test kitchen, you can do that. And of course, we have our mascot with his Twitter. Follow him out on Twitter. No stickers, sadly. I can't send you to the booth. I'd send you to the booth, but by the time you're watching this, no stickers. I'm sorry. And final thought, if you think OpenZiti is cool, if you want to help us get the word out to the world, go out and give us a star on the OpenZiti/Ziti repo. Currently, we have 139. I'm getting word. We have 153 stars on GitHub right now. Really does help us by getting the word out to other developers that, adding OpenZiti into your application is easy. It gives your app superpowers, like I talked about, and it is just smart from the application's perspective. Bring all that zero trust goodness right into your SDK or right into your application itself. And that will complete my presentation. Thanks again to Open Source 101 for having me. I appreciate the opportunity. Cheers.